we are going to talk about the electric potential. And I'm going to really do two things. I'm going to derive the change in electric potential due to a constant electric field, and then I'm going to derive the change in electric potential due to a point charge. And I'm not going to use calculus. Okay, so this is no calculus involved. And so at this point, you should know what the electric field is. I'm going to assume that you know what the electric field is. And as a review, we're going to start off talking about the gravitational field. And I think it's an easy way to get into electric potential. Okay, so here I have a ball at position y1, and it's going to move down here to y2. And these arrows represent a constant gravitational field. The gravitational field is constant near the surface of the Earth, and it has a value of 0, negative 9.80 newtons per kilogram. Newtons per kilogram. Okay, so if I let this thing drop with an initial velocity of v1 equals 0 meters per second, that's the magnitude, then what's the velocity going to be down here? Well, we would use the work energy principle. So we'd say work is the change in energy. And in this case, I'm going to have the work done by the gravitational force. So there's an mg gravitational force on that. And we define work as the work done by force is equal to F dot delta R. So that's the dot product. Just as a review, if I have vector A as AX, AY, AZ, and vector B is BX, so it has components, BY, BZ, then the dot product A dot B is going to be the scalar value of AX times BX plus AY times, that's a Y, times BY plus AZ times BZ. So you take the X components, you multiply them together, and you take the Y components, you multiply them together, and then add that to the X components multiplied together, and the Z components multiplied together. If it's two dimensions, if the Z components are 0, it just makes it easier. Now there is another formula for this. A dot B equals the magnitude of A times the magnitude of B times the cosine of the angle between them. Those are the two definitions of the dot product. I mean, I would hope you've seen that in your previous physics course. If you haven't, that's okay. Okay, we can figure it out now. It's not a big deal. Okay, so but that's the work done by gravity is F dot delta R. So in this case, let's say this is my delta R vector. So delta R is going to be the vector 0, y2 minus y1, right, 0. So if it's moving down, this y2 minus y1 is a negative value. And then the gravitational force mg is going to be equal to 0, negative mg, 0. So I can calculate the work. It would just be equal to negative mg times y2 minus y1, and that would be equal to the change in kinetic energy. Okay, that's the work energy principle. Now, it turns out that it doesn't matter what path you take to get down here. If I go this way, it's going to be the same work done by gravity. If I do this way, it's going to be the same work done by gravity. So in that case, we can actually take that work done by gravity and move it to the other side of the equation and call it an energy. So we say the change in gravitational potential energy is negative the work done by F dot delta R for any force that's conservative, that doesn't depend on the path. So in this case, that would be negative mg, so it'd be negative mg delta y. So the change in gravitational potential energy is mgy. Now, change, remember the delta means change, and change is important here. Oh, delta y. I just said change is important, I dropped it out. That was not cool. Don't do that. Okay. Now, oftentimes, we will say things like, oh, well, the gravitational potential energy is mgy. Well, okay, that's true, but it doesn't matter, right? We never have single values for potential, because I could move the origin wherever I want and I'd have a different potential, but I have the same change in potential. So it's a change in potential that really matters, not the potential. Now, one last thing. What if I did the change in potential energy per mass? That would just be gy. And that would, we could call that the potential. it would be it's like the gravitational potential energy per unit mass, since gravitational potential energy depends on mass. Okay, let's do the problem again. Now let's say I have this. This is two charged plates, parallel plates, and these, when you have these fairly close together, they make a constant electric field. And it doesn't really matter what that value is. I can pick, let's say it's going in the negative y direction for fun, so I can say 0, negative 2, 0 newtons per coulomb. That's my electric field. Okay, I just made that up. Can you tell it's made that up? You should be able to tell I just made that up. Okay. Now, what if I want to go from here to there? Well, I can do the work done by the electric field, right? Because the electric force, F, is going to be, let's say this is charge Q, it's going to be Q times E, so there's my electric force. And then let's say this is my delta R, like that. Well, if I go in a different path, here's one path. I could go this way. Oh, let's write that out. So work is going to be Q times E dot delta R. And you could write that as Q E delta R cosine 0, because delta R and E are in the same direction. Now, but what if I went this way, and then that way, and then this way? Along this path, the electric field and the electric force and the displacement is 90 degrees, so the cosine of 90 is 0. And the same thing's true down here. So the only part that counts is this. And in that part, the electric field's the same value as over here, so you'd get the same thing. So it is path independent. So that means that I can actually move that to the other side, and I get the following for the change in electric potential energy. It would be negative Q E delta R. Let's do it the right way. And this is for a constant electric field only. Okay, so a lot of times you'll see it written just like that, or delta U equals negative Q E. You'll see it like that sometimes, but that's a terrible way. S, where the S is the distance. I mean, I get it, it's okay, but it'd be better to write it as negative Q E delta R. And so why is that negative there? That negative there is because we did the work done by the electric field, we moved it over to the other side, and that's how we got it. Okay, so now what if I take that electric potential, delta U, electric potential energy, and divide by that charge Q? I would get negative E delta R, and we call this the change in electric potential. So we have two things, delta V, electric potential. I ran out of room there, look at that. Delta U is electric potential energy. And so it's really easy to mix those two up, right? But the potential energy has units of joules, and this has units of joules per coulomb. And we call a joule per coulomb 1 joule per coulomb is equal to 1 volt. So when you have a voltmeter, and I had one right here, that's what that measures. When you have a battery, why does it shake like that? It's a different camera. When you have a battery, 1.5 volts is the change in electric potential across those terminals. And we'll talk about that more later, but that's what that is. So the change in potential energy divided by the charge is the change in potential. So then I could put some different charge there and have the same change in electric potential, but have a different change in potential energy. And so this is the, where did I write it? So delta V equals negative E dot delta R for constant E. Only. Okay, now what about a point charge? So we did the electric field due to a point charge. So let's say that I have a point charge right here, and it's at the origin. And now I want, if I wanted to find the change in potential going from point here to point there, it's not so easy, right? Because as I get further away, the electric field decreases. The value of the electric field due to a point charge, is a charge Q, is K times Q over the magnitude of R squared R hat. So if this is some location over here, and that's the vector R, and that's the vector R hat, then that would be my value of the electric field. It points away from the charge if it's positive, and it decreases with distance squared. That's important. But that means that I can't use this. Delta V equals negative E dot delta R, because E is not constant, right? Going from here, the electric field would be like that. Right here, the electric field would be like that. So you'll see this for the electric potential for a point charge. They'll say this. They'll say V equals, and when I say they, I mean just about every single book out there. V equals K Q over R. And that is the potential due to a point charge. But you should look at that and say, hey, wait a second. You just said it was the change in potential that matters. And that's not a change. And you're right. Really, it's this. V, delta V equals, K Q over R. And this is with respect to infinity. So this says that R is my second point. The first point is at R equals infinity. So what if I start way over here and I want to find the change in potential coming all the way over to some position R? This is what it should give me. And we're going to do this, okay? So it's kind of hard to do because I'd have to calculate the electric field way out here and then move it, and the electric field changes. So what I'm going to do is to break it into pieces. I'm not going to start at infinity. I'm going to start far, and then I'm going to move a distance, and I'm going to assume that electric field's constant, and then I can calculate the change in potential over that short time, over that short distance. And then I can do it again right here, and again, until I get to distance R. And we can see if we get the same thing as this. Okay, so let's do that. Now, in order to do this, I need some numbers. So I'm going to take a, let's say, what I picked a value before. What did I pick for my value? I picked Q is 1 nanocoulomb, and I want to go to a distance of R equals 0.1 meters, so 10 centimeters. So I'm going to start somewhere over here. Let's start at, let's say, 3 meters, which is, that's, if I'm going from 3 to 10 centimeters, that's as far as I want it to go, right? We can change that. So I'm going to start at 3 meters, and then I'm going to move a distance of 1 millimeter, so 0.001 meters. And over that distance, I'm going to assume that the electric field is constant. And so with that, I can calculate the change in potential, and then I'll just do it again and again until I get to this location right there. Okay, so I'm going to do this in Python. So if you haven't done Python yet, that's fine. Let me switch over to Python. Okay, so here we are. Okay. So let's just jump into this. I'm not going to give you a big introduction to Python because I'm really just trying to show you how this works. So I'm going to start with my electric constant, K, 9 times 10 to the 9th. I need my charge, Q, is 1 times 10 to the negative 9th. And then I need, okay, so now I need my starting position. My starting position, I'm going to say, I'm going to do this in vectors, okay? So R equals vector 3, 0, 0. So I'm going to start on the x-axis, and I'm going to move my way in until I get to 10 centimeters. Now I need my step size. So I'm going to say dr is my delta r. How far am I going to move? And I said it's going to move a millimeter towards the origin. So I'm going to say this is vector, you got to spell it right, negative 0.00100. Right, because I need to know how I'm moving each time. I need to know how to change my value of r each time. Okay, now I need my final location. I'll call this RF. And this is just the x value, right? So this is the distance, 0.1. And then I need my potential. V, this is big enough? There. V equals 0. So I'm going to start at v equals 0. And that's one of the things when we start with a potential with respect to infinity. I'm going to assume, since the electric field is 0 out there, I'm going to set the electric potential at infinity to be equal to 0. And it just kind of makes sense. I mean, you could put some other value there, but that would just be making things more complicated than it has to be. I don't want to make things more complicated than it has to be. Do you? Okay, you don't either. Okay. So we're going to set it at equal to 0, and that's what we're going to do. So now I'm going to do a loop. So in this loop, I'm going to say while r dot x is greater than rf. So r dot x is the x component of my vector r. Remember, r is where I'm at that particular point. So I'm going to keep doing this until I get to the position rf. So r dot x starts at 3, and I'm going to subtract a millimeter each time, which, yes, I'm going to have to do a lot of calculations. That's why I'm making Python do it, right? Okay, so the first thing I'm going to do is calculate the electric field at that location. So it's going to be k times q times norm r. Okay, so if you remember, norm r in Python is a unit vector in the direction of r. So I don't have to do that. I mean, you could just say x hat, right? I know the direction of electric field, but I'm going to just do this in the most formal way. And then I'm going to divide by the magnitude of this this r value squared. So that'd be mag is a built-in function in Python that returns the magnitude. It's a built-in function in GlowScript Python that returns the magnitude of the vector r. So that's my electric field. I'm going to assume that's constant during this time. So now I can say dv equals negative dot e dr. So dot is the dot product. It's built into Python. I don't have to do it manually. I could do it, right? I could say the magnitude of e times the magnitude of dr times the cosine of the angle between them, or I can even do it e dot x dot times dr dot x plus e dot y, dr dot y, e dot z, and so forth. But it does it for me. So that's the change in potential over that short time, that short distance. Now I can add that to my potential, so I can say v equals v plus dv. So this is Python telling it, hey, take that value of dv, take the value of v, which starts off at 0, add those two together, and make that the new v. So this updates the value of v. You know, the equal sign in Python is not an algebraic equal sign, so don't think that the v's cancel. They don't cancel. Now I need to move my position, my r value, so I can say r equals r plus dr. So it's going to move it more to the left. And that's it, right? So once I get done, I'm going to say print v equals v volts. Now let's do this. Let's also Vt. That's the theoretical value for the electric potential. That's just going to be K times Q divided by Rf, right? So KQ over R is the electric potential due to a point charge. Notice there's not a negative sign there, right? There's not a negative sign. And let's print that out too. Let's say Vt, so we can see how close this is, because we're making some assumptions. Vt volts. And I should save it, and I will give you the code. Electric potential due to point charge. Save. Save. I don't know why it never saves. Why is that problem saving? There, it's saved. Okay. It's just slow. Okay, so you see what we get here. I get a potential by assuming the electric field's constant during each of those distance steps. I get 87.452 volts, and the theoretical would be 90. That's pretty close. Okay, let's just change it up. Let's see, what if I start further away? What if I start at R equals, let's say, 5? Oh, I don't want to run it. Okay, so that didn't help it that much, right? Let's go back to 3. And let's make the step size smaller, just to see what will happen. So I'm going to make it half as big, so 0.5. That's really small. Oh, that didn't help. Okay. Well, let's make it 0.1. Okay, well, it depends on, I guess, kind of surprised it didn't help. Let's just change this to 4. Okay. So now I think it was erring on the wrong side. And if I move further and further away, I think we'll start getting a better answer. Let's put this at 5, and then I'm not going to change again because I don't want it to. Yeah, okay, it's getting closer. So I could keep moving further and further away, and it'd be closer to that. Because remember, I'm approximating where is electric field equal to 0, which is at infinity. Well, I'm not going to start at infinity. It would run forever. But it does run pretty fast. I'm pretty surprised. Okay, let's just make a graph. Look, what the heck? We're going to make a graph. So I want to make a graph of v as a function of r, and, I guess that's kind of difficult. No, I can do that. I can do that. Because as I move closer and closer and closer, actually what I'm going to do is I don't want to plot from 5 to 0.1. Let's go from 0.5 to 0.1. Okay, so let's do this. While the Rx is greater than 0.5, do this. And then after that, I'm going to plot it, right? So I'm not going to plot the first part, so it won't look good. So let's make a graph. In Python, it's easy to make a graph. I could say G1 equals graph, title equals electric potential. That's fine. Due to point. I can give it an X title. And, ooh, you got to spell it right. Title. And that's going to be, let's just say R. And then a Y title. And that's going to be equal to V in volts. And then F1 equals G curve. Color equals color dot blue. Label equals I'm just going to say num for numerical calculation. And then F2 equals G curve. I'm going to plot both of these. G curve color, color equals color dot red. And label equals theory. Okay, that's the theoretical value. So now down here, I didn't plot it in that first part. Now I am going to plot it. So I'm going to say, I'll just copy the exact same thing, right? I'm going to do all the same stuff. Instead, I'm going to say while r dot x is greater than rf. And then down here, I'm going to plot. So I'm going to say f1 dot plot r dot x, right? I should really do mag r. I can't plot r because r is a vector. And then I can say v. Yeah. And then f2 dot plot mag r. This is the theoretical. And then I can just type in k times q divided by mag r. I think that should work. Let's see. Yeah, there you go. So you can see as I get really close, they're pretty close, right? They're pretty close in value, and they give this 1 over r type graph. And so I'm pretty happy, and I think I'm just going to stop there. But I mean, I think the important thing to remember is what is electric potential? And when you get this electric potential to point charge, but it's really, you really find that by doing an integration, right? And this is what, we did an integration. If you haven't done calculus before, that's fine, because we just did it. We just did it by having very, very small p sizes. In calculus, you take the limit as those p sizes actually go to 0, so you get an infinite number of pieces, but it still works out. So there you go, electric potential due to a point charge, electric potential due to the change in electric potential due to a point charge, due to a constant electric field, and the electric potential with respect to infinity due to a point charge. I'll give you the code down below.